Hello everyone. In this video we look at the concept of common ion effect with regard to the solubility of salts. Now we already discussed how common ion effect is going to work in case of the dissociation of an acid or a base in the presence of water, and dissociation of either an acid or a base in the presence of another acid or another base. So these are the two cases where we talked about the common ion effect. Now in this video we'll talk about the common ion effect in case of solubility of salts. So if you look at the common ion effect in case of the solubility, so what is the idea of solubility that we are discussing? If we have a sparingly soluble salt, let's say for example we talk about any salt, let's say we have AgCl, sparingly soluble salt, solid state, it is going to dissolve partially and it is going to give us Ag plus ions in the aqueous state and Cl minus ions. This is what is the solubility of a sparingly soluble salt, and these are the ions that are produced as a result of the solubility, and these ions are produced, they are present in where? They are present in the solution. Now what happens as a result of common ion is, if say for example along with AgCl there is one more sparingly soluble salt or one more highly soluble salt which is also dissolving in the same solution, let us say that is also able to produce Ag plus ions. In this case we will call Ag plus ion will be what? We will be calling it as a common ion. Now as a result of the common ion effect, what is going to happen is the solubility or the equilibrium in the case of the solubility will be pushed in the reverse direction. Means the overall solubility of the salt is going to be decreased as per the idea of Le-Chatelier principles. If for any reaction or phenomena we are adding product, means what is going to happen? The reaction will be pushed backwards, or the phenomena will be pushed backwards. So as a result of common ion effect in case of solubility, what we will be observing is the solubility of the salts is going to be decreasing. So this is the outcome of the common ion effect. So if we have a salt which is dissolving in pure water, the value of S will be higher. If there is a common ion effect in case of the dissolution, means the value of S in that case will be less. So what we see is the molar solubility is going to change. The molar solubility part is going to change. And for any given salt, the solubility product Ksp, right, it's going to be a function of temperature, means it will not be changing. The presence of common ion is only going to affect what? It is only going to affect the molar solubility, and the Ksp value of the given salt will be depending upon the temperature, it will be always a constant. And here the common ion effect we will see in two scenarios. One is if you have a sparingly soluble salt which is dissolving in the presence of a highly soluble salt. The second case will be if you have two sparingly soluble salts which are having a common ion. So these are the two cases we will be considering in case of the common ion effect for the solubility. So let's start with the first case. What is the first case? If you have a highly soluble salt, like say for example we have NaCl, sodium chloride, with a sparingly soluble salt, let's say for example AgCl. In this case, let C1 is the concentration of NaCl. Since this is a highly soluble salt, what is going to happen? The entire amount of NaCl will be dissolved. So we will be getting what? Na plus ions and Cl minus ions. If C1 is the concentration of NaCl we are taking, means the entire amount is going to be dissolved and we'll get C1 concentration of Na plus ions and C1 concentration of Cl minus. Now in addition to that, there is also the solubility of the AgCl that is happening, but this is going to be going through an equilibrium. So it is going to give us what? Ag plus ions and the Cl minus ions. So here if we talk about the solubility as S, then as per the equation, right, if one particle of AgCl is dissociated, it is going to give us what? One Ag plus ion and one Cl minus. So here if S is dissolved, then the amount of Ag plus that is going to come is what? S moles per liter. The amount of Cl minus that is going to come will be S moles per liter. So the final ions concentration will be what? Ag plus will be S, but Cl minus will be S plus C1. Why S plus C1? Because the Cl minus is also coming from the dissociation of NaCl. So if we look at the overall Ksp formula, right, for the AgCl, what is the Ksp formula? It is nothing but Ag plus concentration into Cl minus ion concentration will be equal to what? S into S plus C1. So this is going to give us what is the new solubility value. So normally if just the AgCl alone is dissociating, right, what we are going to be having? We'll be having S into S will be equal to what? Ksp, if just we are having the AgCl which is getting dissolved in water, because the ions concentration Ag plus will be S, Cl minus also will be S. So S into S will be Ksp value. That is the relation. But now because of common ion, right, the Cl minus ion concentration will be what? S coming from the solubility of the AgCl plus C1. C1 is the part coming from the dissolution of NaCl. And sometimes what happens is, if the C1 value is very high in comparison to S, then in this S plus C1 we can neglect it. So we can neglect the S value, because if it is small, so we'll have a simplified formula, and when we will use it, it will be equal to what? S into C1. When we will use it? When the concentration of the ion, common ion coming from the highly soluble salt is very high amount in comparison to the S values. If the order is too different, right, then we can have the simplified formula. So this is how we are going to be having the first case, which is the highly soluble salt with a sparingly soluble salt. This is a common ion effect in case of highly soluble salt with sparingly soluble salt. So we look at some examples on this, then we will be able to understand it. Now let us go to the next case. What is the case 2? It is the case of two sparingly soluble salts. So what is it going to be like? Say for example, we have AgCl and AgCN. These are the two sparingly soluble salts. This is getting dissolved. It is going to give us what? Ag plus and Cl minus. This is going to dissolve, means it's an equilibrium. So it is going to give us what? Ag plus and Cn minus. Here what is the common ion? Ag plus ions are basically the common ions. So if the solubility here is say for example S1, the amount of Ag plus added will be what? S1. Amount of Cl minus will be what? S1. If the solubility here is S2, then the amount of Ag plus added will be what? S2. Amount of Cl minus in the solution also will be what? S2. So if you look at the molar concentrations of Ag plus in the solution, overall solution we're talking about, will be S1 plus S2. Why S1 plus S2? Because Ag plus is coming from the dissolution of AgCl. Ag plus is also coming from the dissolution of AgCN. It is coming from silver chloride dissolution as well as silver cyanide. So we have to add both the amounts. Whereas the Cl minus concentration will be simply S1 only. Here also Ag plus concentration we have to add S2 and S1. So it will be what? S1 plus S2. And cyanide and concentration will be what? Simply S2 only. So for this AgCl, we'll have the Ksp formula. Ksp for AgCl, right, will be equal to what? Ag plus ion concentration, which is S1 plus S2 into Cl minus concentration S1. This is equation 1. Silver cyanide Ksp value for the silver cyanide. What will be the value? Ag plus concentration into cyanide ion concentration, which is S1 plus S2 into S2. So this is like equation 2. So here we have two unknown variables, S1 and S2 are the unknown variables. By solving these, and Ksp values will be given to us. By solving these two, we will be able to find what? S1 and S2, which are the molar solubilities of both these salts, silver cyanide and silver chloride. Now if we have the salts of different formula, the number of ions produced here will be different, and the Ksp might have the ions raised to the ion concentrations raised to the powers, because the Ksp formula will be what? The product of concentrations of ions raised to the suitable powers. So there might be some changes in the examples like that, but this is the broad idea. What we have to do in the Ksp formula of each of these salts, we have to add the ions concentration coming from both the sides. That's it. We basically have to add the ions concentrations coming from both the parts. So this is about the common ion effect in case of two sparingly soluble salts. Okay, now we'll go and take a look at some questions. Look at this first question. Calculate the molar solubility, means we have to find what? S of nickel hydroxide in 0.1 molar sodium hydroxide. So nickel hydroxide is it is dissolving in water along with the sodium hydroxide. The Ksp of nickel hydroxide is what? 2 into 10 power minus 15. The Ksp value for the nickel hydroxide is what? 2 into 10 power minus 15. Okay, so we must get the answer as what? 2 into 10 power minus 13. So final answer for S must be coming as what? 2 into 10 power minus 13. So let us see. We have nickel hydroxide. If it is getting dissolved, what we are going to get? We are going to get nickel 2 plus ions and 2 OH minus ions. Let us say S is the molar solubility. Then for every one particle of nickel hydroxide dissolved, we will get what? 1 Na2 plus ions, means the concentration of nickel going to come is what? S. And for every one particle here, we are getting how many OH minus ions? 2 OH minus ions, means the amount will be what? 2S here. The overall concentrations of nickel 2 plus will be what? S. And hydroxide and concentrations will be 2S plus something. What is this something? The something is going to be the part of OH minus coming from the dissolution of sodium hydroxide. What is sodium hydroxide? It is a substance which is going to completely dissolve. It is going to give us what? Na plus and then OH minus. It is a strong electrolyte. If you are adding 0.1 molar, means it is going to give what? Same 0.1 molar of Na plus ions and 0.1 molar of OH minus. So the concentration of hydroxide ions will be what? Hydroxyl ions will be what? 2S plus 0.1. This is the concentration of OH minus ions. Now what is the Ksp formula? Ksp will be equal to what? S into 2S plus 0.1 the whole square. Why the whole square? Because for the nickel 2 plus ion, what is the coefficient? 1. So nickel 2 plus concentration power 1, like that. And OH minus, what is the coefficient here? 2. So OH minus ion concentration square. Now in this, right, if you look at the Ksp value is in what range? 10 power minus 15, means it is a sparingly soluble salt. So the value of S will be negligible in comparison to what? In comparison to the amount of the OH minus concentration coming from the NaOH dissociation. Means in this, right, 2S plus 0.1 we can neglect 2S value because it will be small. So as a result, what we will be having is Ksp, which is 2 into 10 power minus 15 will be equal to what? S into 0.1 the square. 0.1 the square means what? S into 0.01. So 2 in 10 power minus 15 is equal to S into 0.01, means S will be equal to what? 2 into 10 power minus 15 by 0.01, which is 2 into 10 power minus 13. So that is the value of S, and that is what is the molar solubility of nickel hydroxide. So this molar solubility value, right, will be lesser than what is the molar solubility of the same nickel hydroxide in pure water. If the same nickel hydroxide is getting dissolved in pure water, right, whatever is that molar solubility value, that is going to be higher than the value we are getting here. What is the value that we are getting here? 2 in 10 power minus 13. So always a common effect, right, is going to do what? It is going to decrease the molar solubility. Clear? So what we are doing in this question, we are simply taking whatever is the OH minus ion concentration coming from the NaOH dissociation and simply adding it to the OH minus concentration coming from the nickel hydroxide dissolution, so that this is the overall concentration. And in that we are doing simplification. Why are we able to do the simplification? Because if you look at the Ksp value, it is in very 10 power minus 15 power, whereas the OH minus coming from the NaOH is what? 0.1. So we can neglect this 2S value in comparison to 0.1. Thereby we are getting approximate value of S in this case is what? 2 in 10 power minus 30. So this is how we'll have the common ion effect problems in case of the solubility of the salts. So we look at one more question. Calculate the solubility of silver carbonate. What is silver carbonate? Ag2CO3. Calculate the solubility of silver carbonate in 0.25 molar solution of sodium carbonate. What is sodium carbonate? Na2CO3. The solubility product of silver carbonate in pure water is given as what? 8.45 in 10 power minus 12 at 25 degrees centigrade. Remember what we said, for any substance solubility product is not going to change. It is going to change only when we change the temperature. So what is the Ksp value for the silver carbonate Ag2CO3? What is the value? 8.45 into 10 power minus 12. This is going to be as it is. Now if you look at the dissolving of silver carbonate, what we'll see, if S is the molar solubility, it is going to give us what, 2 Ag plus ions and CO3 2 minus ions. So for every one particle of Ag to CO3, we'll get how many Ag plus ions? 2 Ag plus ions are going to come. So the amount that is going to be added for the Ag plus ion concentration will be what? 2 times S, means it is going to be 2S. And for every one Ag to CO3 particle, how many carbonate ions are getting released? Only one is getting released. Means if S is dissolved here, means we are going to get how much? S amount of carbonate ions. So the Ag plus ions concentration will be what? 2S, and CO3 2 minus ion concentration will be S plus something. Why this something is going to come? Because we are having the common ion effect. What is the common ion effect here? The carbonate ion is also coming from where? Na2CO3 dissociation. Na2CO3 is what? It is a strong electrolyte. Means whatever Na2CO3, it is going to dissociate into what? 2 Na plus and CO3 2 minus. Every one molecule gives what? 1 carbonate ion. What is the concentration of Na2CO3? 0.25 molar. Means the concentration of CO3 2 minus coming from here will be what? 0.25 molar. So we have to add 0.25 to S. So this is the overall concentration of CO3 2 minus. Here also we have the sparingly soluble salt with an highly soluble salt like sodium carbonate. Now what is the Ksp value? Ksp value is given as what? 8.45 into 10 power minus 12. Okay, Ksp is equal to what? Ag plus concentration power 2. Why power 2? Because the factor here is what? 2. Means 2S square into carbonate ion concentration power 1. Means simply carbonate ion concentration. What is carbonate ion concentration? S plus 0.25. So here if you look at the Ksp value order is what? 10 power minus 12. And what is the concentration of carbonate ion coming from the Na2CO3? 0.25. Means the S value will be small in comparison to 0.25. So we can neglect the value of S when we are adding it to what? 0.25. So we'll simplify it as what? 8.45 into 10 power minus 12 is equal to 2S the whole square, means what? 4S square into this we are neglecting, this S is neglecting, into the remaining will be what? 0.25 means what? It's basically 1 by 4. 0.25 means 1 by 4. The 4 will be cancelled. Means S square is equal to 8.45 into 10 power minus 12. So S will be equal to what? Root 8.45. Root 10 power minus 12 means what? 10 power minus 6. So root of 8.45 will be approximately, because root 9 means what? 3. Root of 8.45 means it will be somewhere close to 2.9. So what is the answer? 2.9 into 10 power minus 6. So this is the value of the solubility of silver carbonate in 0.25 molar solution of sodium carbonate. So here we have the same procedure. We are adding the concentration of carbonate ion coming from the Na2CO3 dissolution, and we are simplifying it. Why? Because whenever we are simplifying, how we are able to simplify? We are checking the order of Ksp. It is very small. So we are neglecting the concentration of carbonate ion coming from the dissolution of the sparingly soluble salt, and then we are getting the approximate value for the solubility value S. So this is how we are going to look at the common ion effect in case of the solubility of the salts. So this is the last idea of the chapter, and this ionic equilibrium, right, is in a way important for some chapters in plus 2, like the electrochemistry. There also we are going to be talking and using some of the things that we discussed in the electrochemistry, especially the dissociation, degree of dissociation concept, and even the solubility, hydrolysis. So all these things we will be using again in electrochemistry chapter. So as a whole, right, this is a very important topic for the competitive examinations, especially JEE Advanced and even JEE Mains. It's got good weightage. More than the chemical equilibrium, most of the times they will prefer giving questions on the ionic equilibrium. So make sure that you go through the concept thoroughly, especially the idea of common ion effect. How do we use it? If you are able to understand that part clearly, means most of the ionic equilibrium chapter will be good, because otherwise the general idea of equilibrium, right, is very much similar to what we have seen in the chemical equilibrium concept. Only additional thing that we are learning here is the pH measurements and the concept of common ion effect. Okay, so we'll see in the next chapter.